Hello, and in this problem we are going to do another proof. This is a proof in two parts, and we will be using the forward-backward method for each part. However, I'm not going to show you all the details needed to construct the proof. We're just going to get right into the proof. Okay, so reading this problem, let ax equals b be any consistent. What does consistent mean? Because consistent means it has at least one solution. Ax equals b be any consistent system of linear equations, and let x1 be a fixed solution. So that means that a of x1 is equal to b. Prove that there's our key word right there, every solution to the system can be written in the form x equals x1 plus x naught, where x naught is a solution to ax equals 0. So we also know that ax naught is equal to 0. Okay, so that's part one. We're going to do this in two parts. Prove that every solution to the system can be written in the form x equals x1 plus x naught, where x naught is a solution to ax equals 0. So that's part one. And then part two, we're going to prove that every matrix of this form, and by this form they mean x equals x1 plus x naught, is also a solution. Okay, so in this problem I might say vector when I mean matrix, but because this is a vector, x is a vector, we could also call it a matrix. I might use those words interchangeably. Okay, so we'll start with part one, and then we'll prove part two. The two parts might sound very similar, but they're not. They're a little bit different. In part one, we're going to give a solution. It says that every solution, but we have a solution. Let's say ax equals b. So we have a solution x. And then we have to show that that solution can be written as x1 plus x naught. So that's part one. We have to give a general solution, x, and then show, or in this case prove, that that solution is equal to x1 plus x naught. And then the way part two is different because we assume we have a matrix in the form x equals x naught plus x1, and we're going to show that that's a solution. Okay, so let's go ahead and prove part one. For part one, we're going to identify our hypothesis and our conclusion. So the hypothesis is that ax equals b is consistent, which means it has at least one solution. x1 is a fixed solution. So we know that ax1 equals b. And we also know that x naught is a solution, and I'll refer to this as the homogeneous solution. ax naught equals 0. And then our conclusion, the thing we're trying to prove, is that there's our keyword, every solution to ax equals b can be written in the form x equals x1 plus x naught. Okay, so let's go through the forward-backward method, starting with the conclusion. The key question, or the key thing we have to answer here, the key question is, how do we show that every solution can be written in this form? Okay, so right now I want you to convince yourself that if ax equals b has one solution, then x1 and x0 are the same, right? If it has one solution, then it's not going to have two different answers. But if it has an infinite number of solutions, we want to show that we can get a third solution by adding x1 and x0. But we want to show that every single solution that we can create can be written in that form, x1 plus x0. So to answer this question, we're going to start by choosing a solution. This is called a choose method. We're just going to choose one, okay? So choose x, that is a solution. And then we have to show that x is the sum of the other two, x1 plus x0. If we can do that, then we've just shown that every solution can be written in that form. Okay, so this leads to our statement B1. B1, we're going to show that x1 plus x0 is a solution to ax equals b. And what do we have to do before that? Well, if we show that it's a solution, we're done. But what do we have to know about x1 plus x0? We have to know that that came from a prior solution, which we call x. So this leads us to our next step, which is B2. We have to show that x, which was the previous solution, must be x1 plus x0. Okay, so that should be it for our backwards part of the proof. We're kind of stuck there. Let's see what we can do in the forward part. So we know up here that ax equals b is consistent, and we know two solutions. So we'll use those facts to have those two solutions. And then from there, we'll create a new solution. We'll assume we have a third solution. And then we should match up with B2 at that point. Show that the solution we get must be x1 plus x0. So here's statement A1. A1, we're going to use the fact that x1 and x0 are solutions to ax equals b and ax equals 0, respectively. And then we are going to have another vector x, also x, which is just some general vector, is another solution to ax equals b. And then what do we have to do before that? After that, excuse me. We're going forwards. So what do we have to do after that? We have to create a vector. And here's where we get a little bit clever. So we know that what x is, so based on x, we have to do something to it. So we know that ax equals b is a solution. So if we create a vector x, we got to do a little bit of math here. So I know that x is equal to x1 plus x naught, but we want to do something to x. What we can do is subtract from it. We can subtract x1 from both sides. So we have x minus x1 equals x naught. And the reason we do that is because we have a vector x, and I want to do something to it. So the only thing we can really do here is subtract from it. And then we're going to show that that is a solution. Okay, so there's details in here, which you'll see in the proof. But I'm going to save that because I told you this one's a little bit less hands-on than the previous proof. Okay, so here's our plan of attack. First, I'm going to show, the hypothesis, and then we'll show A1, and then we'll go through A2, and then once I have that vector, I have to show that that vector must be x1 plus x naught, so we have B2, and then we're going to show that that's a solution, B1, and then finally I have my conclusion, which is that we have every solution is in this form. Okay, so we'll see those details in the proof. So here's the proof of part 1. All right, since the matrix AX, or the matrix equation AX equals B, is consistent, we know what about it? We know it has at least one solution. And this problem is way more interesting if we know that AX equals B has an infinite number of solutions. That's what makes this more useful to us. But it also works if it has only one solution. And then we're going to let x1 be a fixed solution. To AX equals B, meaning that AX1 equals B. So we have one solution there. And then we're going to let x naught be a solution to the homogeneous system, which is the one where it's equal to 0. Just throwing in some vocabulary there. Homogeneous system AX equals 0, meaning that A of x naught is equal to 0. Next, we're going to let x be a solution to AX equals B. So here's the part where we get a little bit clever. I know that x is a solution, so I have to do something to x. We're going to choose. I'll put choose in quotes because this is part of a proof technique that you'll learn about later. Choose a vector that is the difference x minus x1. So that's something we've created, and we're going to show that that is going to lead us to the x being equal to x1 plus x naught. By substitution, we can go ahead and plug in x1 by x minus x1 in for x, ax minus x1. But I don't know that this is equal to b or what it's equal to yet. I don't know what this is equal to yet. We're going to do a little bit of algebra here to show what it's equal to. So all I did was I plugged it into the left side of the matrix equation. And then this is something we proved in the previous proof. The previous video, I proved the distributive property for matrices. Using the distributive property, and this will be on the left, right? The left distributive property for matrices, we have ax, that's equal to ax minus ax1. And then as defined, as we defined them above, what is ax equal to? Ax is equal to b. So I can go ahead and just say, okay, that's equal to b. And then what's ax1 equal to? Ax1 is also equal to b. That's the way I've defined them. So we have that's equal to b minus b. And if you subtract two vectors that are the equal size, you get the zero vector. Thus, so here's our result. Ax minus x1 is equal to 0. But a times what is also equal to 0? We know that if we multiply a times x naught, we also get 0. So from here, we can let x naught be equal to that difference, x minus x1. Then x naught is a solution to the homogeneous equation, or I should say homogeneous system, ax equals 0. Rewriting x, we have x minus x1 is equal to x naught. We can go ahead and add x1 to both sides, plus x1 plus x1. X is equal to x1 plus x naught is a solution to ax equals b. So we started with a solution x, where ax equals b. And we have shown that x is equal to x1 plus x naught. And therefore, we have shown that every solution to the system can be written in the form x1 plus x naught. So that is the solution to part 1. And we'll get into part 2. Okay, for part 2, it sounds very similar to part 1. We actually have the same exact hypothesis. So for part 2, A is the hypothesis that AX equals B is consistent. It has at least one solution. X1 is a fixed solution. To AX equals B. And X naught is a solution to the homogeneous system AX equals 0. Now B is where it's different. The conclusion here is different. It's a little different than part 1, although it sounds very similar. For this one, we're going to prove that every matrix, or vector, however you want to call it, every vector or matrix of the form x equals x1 plus x naught is a solution to AX equals B. Okay, this one has a very similar leading question. How do we show that every matrix is a solution? So I'm just going to give you on this one I only have an A1 and a B1, and we're just going to get right to it. So starting backwards, B1, we're going to have to show that x equals x1 plus x naught always satisfies the equation AX equals B. Okay, and you can take some time to develop this proof in your own way, but I'm just going through it quickly. A1 will then be the case where we're going to create a vector x equals x1 plus x naught and show, what about it? Show it is a solution to AX equals B. Okay, so from here our plan is to go from A to A1 to B1 to B, and then we're done. This proof's a bit more straightforward than part 1. So here we go. Proof. I'm going to start on the bat by choosing. We have the same assumptions, so I'm not going to repeat the same assumptions as the first proof, but you can go back and look at that one. From here, we're just going to jump to the second step, which is to choose a vector x, which is equal to x1 plus x naught, where x1 and x naught are solutions to the equations AX equals B and AX equals 0, respectively. Okay, so we're going to just plug this in by substitution, which means we're just plugging it in. By substitution, AX is equal to A times, in parentheses, x1 plus x naught. And then where am I going with this? I have to show that this is equal to B. So what can I do next? Yes, we can use the distributive property on the left side for matrix multiplication using the distributive property. And this is left again. The left distributive property for matrices, which we proved in the previous video, we get that that's equal to AX1 plus AX naught. And then what do we know about AX1? AX1 is really the same thing as B. and ax naught is really the same thing as 0. So we're just going to plug in what they're equal to. That's equal to b plus 0. And b plus 0 is really just b. So we have just shown that any vector of the form x1 plus x naught is a solution to which means that x equals x1 plus x naught is a solution to ax equals b. And there's our proof. Okay, I want to show you a consequence. So why do we prove theorems? Well, mathematicians are lazy. Okay, we prove theorems because we can use the results to make our lives easier. So I'm going to show you an example of this proof. Going through all this process, it seems kind of tedious, but once we know it's true, it's always true. So let's go ahead and look at an example. So here's an application of the theorem, or we'll call it a theorem, even though I don't think I called it that, but we'll just go through it. So let's create a matrix A, which is equal to 2, 2, 1, 1. I chose this because it has an infinite number of solutions. And then from here, I'm going to create x naught, which is the homogeneous solution. That is equal to 1 and negative 1. And then x1 is equal to 1, 1. And then I also have a b. B is equal to the vector 4, 2. So you should verify that. A times x naught is equal to 0, and that A times x1 is equal to b. So take a minute, take 30 seconds of your time, pause the video, and verify that those two things are true. Okay, so once you've verified those two, then we're going to create a new vector, which is x. That is going to be equal to x1 plus x naught, which is equal to the vector 1, 1 plus the vector 1, negative 1. So our new vector x is 2, 0. And now we want to show that A times x is equal to b, and we'll just do this with straight matrix multiplication. So we have the matrix 2, 2, 1, 1, and we'll multiply that by the vector, which is the sum 2, 0, the sum of x1 plus x naught. And then just doing straight matrix multiplication, we get row 1 times column 1. 2 times 2 is 4, plus 2 times 0, that's 0. 4 plus 0 is 4. So that's row 1, column 1 of our vector. And then row 2 gets multiplied by column 1. 1 times 2 is 2. 1 times 0 is 0. 2 plus 0 is 2. So we've just verified that our new vector satisfies this equation. Thanks for watching.